Hi, hello everyone. This is your Ragvi Deva. I hope all are doing good. Um Early videos we saw about NMOS logic family, how we are going to implement under the principles of NMOS logic for a logic gates. Today we are going to see about PMOS logics. What is the conditions we saw in NMOS? Revert conditions, as I told earlier. Uh, so PMOS, in order to on the device, we have to provide the input as a 0. Why? Because means for PMOS we are using the bubbles. So for PMOS logic, if you want to enable the transistor on, the input condition to be 0, right? And their NMOS logic, we are considering for dot operations, we have to connect the transistor in a series form in two input condition, two or two more input conditions. For plus means parallel, but PMOS reverse logic we have to take. PMOS is nothing but we are considering upper part of the region. NMOS we are considering lower part of the region. So there we are connecting upper region as depletion mode, lower part as enhancement mode. Here you see the difference. Upper part as enhancement, lower part as depletions. Under depletion conditions, we require only one transistor in order to enable the conditions. So you see, uh, and the logic as A dot B. Truth table as 1 conditions only, the output as 1. You have to satisfy the conditions and you have to construct the design for this logic. Here you see, um, dot means for PMOS conditions it should be in a parallel form. Here we are considering two inputs, A inputs and B inputs. So it to be connected parallelly, right? It to be connected parallel, and it's a upper part of the region. It will be called as a pull-up network. So PMOS is also called as a pull-up network because of, always we are connecting the PMOS in the upper part and NMOS is in the lower part. Here the lower part we are connecting the depletion transistor. The entirely the logic is different from the NMOS, and obviously and gate we have to connected one inverter as the output. So this inverter has to be designed under the PMOS logic. NMOS logic we are using upper part as depletion, lower part as only NMOS. But here for inverter of PMOS, the upper part is PMOS and the lower part is depletion mode of transistor. This is the inverter for PMOS conditions. This is the basic difference. You check the logic. If you provide for A input as 1, 1 means the bubble invert 0, the 0 will be passed to the transistor. A transistor is in a off mode, and B transistor we are providing input 1 means 0, 0 means this transistor will be in off mode. So both A and B is in the off mode conditions. It never provide any logic. Okay, so here the depletion transistor get always on state, no, so it provide the if it is on means it will be passes 0 because here it will be connected to the output and ground terminal. So if it is on means it will be provide the 0 logic to the output. So that output will be passed on to the inverter logic. So that inverter logic it will be passed on to the PMOS. 0 is passed on to the PMOS means the bubble inverter value it enable 1. So 1 means it will be passes VDD to the output. VDD means logic 1. So under the logic 1 conditions it provide the output as 1. Yes, obviously it satisfy my logic. Then we'll check 0 logic. If A value as 0 means the bubble invert and passes 1 to this A transistor. So obviously it will be on. And B as 0 means the bubble invert 1 will be passed on to the transistor and it will be pass VDD. So both the transistor, it will be in on condition, and it will be pass a logic 1 to the output of the inverter. 1 means the bubble invert, 0 will be passed on to this transistor. If it is 0 means this transistor will be in off mode. Once if it is off mode, the depletion transistor get activated. So the depletion is to be connected to the ground to output, so it will be passes 0 to the output. Alright, so 0 to the output. So in this condition 0 0 means we are getting output 0. Yes, obviously it satisfies the logic of AND gate. And you see one more cases, uh, 1 0 logic we are considering, AS1 BS0. So obviously output have to get 0, whether we check whether we are obtaining the output or not. AS1 1 means bubble invert 0, the transistor get off. BS0, the bubble invert 1 is passed on to the transistor. A transistor is an off state, B transistor it will be in a on state. So under it will be parallelly connected. So the VDD may be passed on to either A through A transistor, or either it will be passed on to B transistor, because it's to be parallelly connected one. So here is the way only to pass on VDD to the output is B, because B is on transistor, A is in off mode. So it will be passes VDD to the output of the inverter. So one get pass on to PMOS, this PMOS. So 1 means the bubble invert is 0, the transistor get off, obviously it get enable the depletion mode of transistor. Depletions, the enhancement not get work means the depletions to be activated, consider that depletion mode of transistor value. So it's to be on means it directly passes 0 to the output. So 1 0 conditions also we are getting logic 0, the same wise for 0 1 logic, right? 0 1 means A transistor on, B transistor off, the VDD pass on through A transistor to the output of the inverter. So 1 it will be passed on to the PMOS means the bubble invert 0, so the transistor get off. So the depletion transistor only enable, it passes 0 to the output. So obviously under this design it satisfy the AND gate logic. If you want to design the NAND gate, the same model of design, but the output of the inverter get removed for NAND gate of design, right? So this is an AND gate of design, exact same as AND, but the last part of inverter model we have to remove for NAND gate. This is the logic. AND gate we are connecting inverter as the output. NAND we never no need to connect the inverter at the output. Likewise, OR and NOR. OR gate it requires the inverter at the output. NOR gate never requires the output. Like okay, fine. Now we move on to the complementary metal oxide semiconductor, which is possible combination of both PMOS and NMOS. Because where the situations NMOS is faster than PMOS, but uh, where the situations uh, here uh, it has greater complexity. Both we can design in a single model of design, but the speed of execution is much faster comparatively NMOS and PMOS logic. That's the reason they can give a prefer for that combination model of design, and dissipation is also too less compared with that other model. And one more plus is that it has to provide more fan out condition, that is one input we can get a multiple output possibilities, and it to be act as a better noise margins. So these are the reasons behind that we give much importance for CMOS conditions in a VLSI model of designs. So as you know, the for designing that NMOS logic, dot means series, plus means parallel. For PMOS logic, that reverse conditions, they separately we are designing. For NMOS means we are considering bottom of the transistor, upper part depletion. For PMOS means consider upper part of the transistor, bottom as depletions. But here combination means we have to take a part of enhancement mode alone, not a depletion part. So PMOS is upper part, NMOS is lower part. The same logic we have to follow here for designing that complementary metal oxide simple AND model. For AND logic, what we design for a NMOS, that to be considered the lower part. For AND gate, what we consider for the PMOS, that to be considered in the upper part. And then finally, output for AND logic, we have to connect the inverter. So CMOS inverter as upper part as PMOS, lower part as NMOS. Right? So this is AND. For NAND means the same design without inverter. Last part of inverter design, we are obtaining NAND gate. Like the same principles we have to follow for to designing the NOR gate. OR gate, we have to consider the inverter at the output. NOR gate, we have to remove the inverter at the output. This is the logic we are used for designing the conditions. So I hope all get understands. If you like this video, like, subscribe and share it. Thank you all.